Okay, so we started with actually a 1D case, right? So we start with a 1D case. Okay, and this 1D has actually a unitary matrix A, which we say will act on some sequence U. Okay, and the U is of length n, then A is n cross n, right? So this is like n cross n acting on n cross 1 to give n cross 1, right? And then we said that each of these coefficients, right? So you can express them as inner product of the sequence U with AK star, right? And where these AK stars come from A Hermitian, which is of course A complex conjugate transpose. Okay, and we have taken some size, right, n cross n, and these columns, okay, were your AK star. Okay, and we said that is AK star. Of course, the key thing about these AK stars is that they are no orthonormal. They form an orthonormal basis. So AK star, if you take the inner product with AL star, then this is 0 if k equal this is okay. If k not equal to L, 1 if k equal to L. Okay, and then we said that you can expand U. Okay, of course, one thing is U is A Hermitian V, but that also can be expressed as in terms of a summation as sum over k Vk AK star. Right, all of this is okay. So in terms of 1D, and we would like to. So the idea is to move towards a 2D situation. Okay, move towards 2D from 1D. Towards 2D. Okay. Rather than straight away, jump into a 2D situation. We right? So we want to see if there is a kind of a natural progression, right, that takes you from 1D to. So move towards 2D from 1D. Okay. And we would like to, in fact, utilize the same A. In fact, okay, right? We'd like to see whether we can utilize the same A in order to be able to go there. Okay. If it is a 2D, for example, for an image, right? If you wanted to find a transform, then we would like to see whether this 1D A itself can kind of help you get there, or if it is some other sort of a transform, right, which you would call a 2D unitary transform, then we would still want to know what kind of a relationship it has then, okay, with this guy. And then the other thing is, right, it is not immediately clear as to know how does one write down. For example, if it's a 1D case, then it's clear that I'll have an n cross 1 kind of a vector for U, and then I act A on that, and then I get V as n cross 1. If I had an image, right, it is not clear how I should be writing it. Should I write it as a kind of n square by 1 vector? Then what would it multiply, and why would I know that is it 1D A that is acting on it, or is it really a 2D unitary transform acting on it, right? So those things are not obvious. But yeah, and then right, as we kind of go along, okay, those will all become obvious, hopefully. Okay. Now, prior to going to this, going to what are called the basis images, right? We'll first we'll just look at this Frobenius norm. Did I talk about a matrix Frobenius norm last class? No. Okay, so we all know about it, right? So I'll just mention it here. Okay, this is just for the sake of people that may not be aware. So the Frobenius norm of a matrix. Okay, and of course, as you all know, right, a matrix has several kinds of norms. Okay, one of the commonly used norms is a Frobenius norm. Okay, and what that really means is, so you can have norm of A. Okay, where in order to indicate that it's Frobenius, you'll typically write it as F. Okay, and this is nothing but root of summation of, let's say, if you call the entries of A as Aij, right, then you take a double sum over all entries Ij, and then take the magnitude square. Okay, root of that. And similarly, right, you can also have something like an inner product. When similar to the case of the vectors, right, you can also talk about inner product of two matrices. So where we can have something like inner product A, okay, with B, and that will turn out to be summation, again double sum over whatever Ij. Okay, it need not be square, but they have to be of the same size. Okay, whatever m cross n or whatever, and then Aij, B star Ij. Okay, and of course when A is equal to B, then of course clearly inner product A with itself, right? So A equal to B, this will be like norm, Frobenius norm square, right? And yeah, right. Later, okay, we will also see what is called a spectral norm and all that. But right now, okay, let's be content with because this is what we need, okay, as we go along. Now, okay, for the time being, right? I mean, you just have to kind of go with me. Okay, in order to go to a 2D case, right? I'm going to say that right, we'll do certain operations. Okay, it might actually look a little odd right now. You may wonder why am I doing it, but then along the way, right, as things unfold, okay, it'll be clear why we did what we did. Okay, but right now, okay, you might be wondering why am I doing why am I taking this kind of a product and all that. But okay, for the time being, right, you just have to wait till things unfold. Okay. So what we will do is, let us kind of do a construction, that is construct matrix. I'm going to call this as A star KL, such that it comes as AK star AL star, and this is a transpose. Okay, so this AK star is the same guy. Okay, this is coming from the columns of this one, A Hermitian. Okay, these are those AKs. These are not some arbitrary AKs and all. These are the basis vectors, right, that you had here. Okay, for your A Hermitian. So these are the columns of. Okay, so any A star KL is a matrix now. Okay, which looks like this. Okay, now for example, okay, if you look at okay, so I mean, in order to just make this point more clear, we'll take a small example. Okay, even 3 cross 3 will be slightly messy. So just take a 2 cross 2. So let's call this A00, A01, A10, A11. So just take A to be that. Therefore, A Hermitian becomes A star 00, A star 01, A star 10, A star 11. Okay, so for us, this is like A0 star, this is A1 star. Okay. If you had more, if you had 3 cross 3, then of course you would have had A1, A2, and so on. So I'm just taking the smallest case for which we can easily write things out here. The rest of the things you can always code it in MATLAB, and then you can take whatever size you want, and you can show that all that I say for a 2 cross 2 will all hold. Okay, for whatever be the size. Okay, you can't show all that here; it will become kind of messy. So let's kind of look at A star. Okay, so what this means is that then if I look at A star 0, 0, okay, if I look at A star 0, 0, that is like A0 star into A0 star transpose. Right, this is a complex A0 star transpose. Okay, so what this means is that my A star 0, 0, okay, is equal to, so it's like take this vector, right, and then multiply it with its own row version, right? So this will look like A star 0, 0 into A star 0, 0, A star 0, 0, A star 0, 1, then A star 0, 1, A star 0, 0. So it's like this, no? So A star 0, 0, A star 0, 1 multiplying A star 0, 0, A star 0, 1, right? This is what we're doing. So A0, 0 star A star 0, 0, and then A star 0, 1 is into A star 0, 1. Okay. Now let us look at let's say one more thing, right? Let's say suppose we want to look at A star 0, 1, right? What would that look like? That would be like A0 star into A1 star transpose. So that is A0 star A0 0 star A0 1 star multiplying A1 star transpose. A star 1 0, A star 1 1. Okay, so this gives you a matrix that looks like A star 0 0 into A star 1 0, A star 0 0 into A star 1 1, A star 0 1 into A star 1 0, A star 0 1 into A star 1 1, right? And we know that Similarly, you can have A star 1 0, you can have A star 1 1, right? So you can have four such cases, right, for this A star KL if it is 2 cross 2. So if it is 3 cross 3, you can have 9 cases and so on. Okay. Now, what we are interested in is really, is in this. Suppose we take the inner product of A star, let us say 0 0 with itself. Okay. Suppose we do this. Okay, we take the inner product of A star 0 0 with itself. Now, since we have already seen, right, if you have two matrices, how to take the inner product. So in this case, right, this is going to be a scalar. So we know this is going to be A star 0 0 into A star 0 0 into the complex conjugate of that its own entry, right? So A 0 0 into A 0 0. Correct. You have this guy, no? So A star. So whatever is this guy, right? So we can even keep it on top, right here. Okay, so it's here. So then we'll have plus. Then the next entry is, let's say, A star 0 0, A star 0 1. Then its complex conjugate A 0 0, A 0 1 plus A star 0 1, A star 0 0 into A 0 1, A 0 0. Finally, plus A star 0 1, A star 0 1, A 0 1 into A 0 1. Correct? Okay, so now, right, if you were to further simplify this, right, so this first term is what? No, I'm just saying the first term. Okay, first term is not 1. The first term is simply magnitude A naught naught to the power 4. Okay, so this is like magnitude A naught naught to the power 4. Then this is magnitude A naught naught square into magnitude A01 square. Then plus magnitude A naught 1 square, magnitude A naught naught square, plus this is magnitude A naught 1 to the power 4. So if you look at it, right, these two are exactly identical, no? These two are the same. So this magnitude A naught naught to the power 4 plus 2 magnitude A naught naught square into A naught square plus magnitude A naught 1 to the power 4. This is nothing but magnitude A naught naught square plus magnitude A naught 1's square, the whole square. Correct. But then we know that magnitude A naught naught square plus magnitude A naught 1 square is but the norm square of A naught star, right? Because if you look at this guy, right, A naught star is sitting here. Okay, this is what we called as A naught star, right? This one is A naught star. So if you look at its norm, that is magnitude norm square is magnitude A naught square plus magnitude A naught 1 square. But then we know from this other relation, right, that we had, you know that this right, we saw here. No, right, they write that. Yeah, here, right. We know that if you take norm of each one of them, these form an orthonormal basis, right? So they all have length 1. Okay, so what this means is that this kind of boils down to 1. Okay, so the answer is correct. I mean, somebody said 1, but after you show this, okay, not the first term is not 1, but once you collect all the terms, turns out that the direct inner product of A star 0 0 with itself is 1. What about inner product of, let's say, what was the other matrix that we wrote down there? Some 1 0 something, no? 0 1. Okay. So let's look at A star 0 0 with A star 0 1. Okay. If we had to look at what would this give, then let's just go back to that. Okay, we are right there. So what will that entail now? A 0 0 star, okay, into 0 star. So A 0 1 is here, so that's A 0 0 into A 1 0 plus A star 0 0, A star 0 1, A 0 0, A 1 1 plus A star 0 1, A star 0 0 into A 0 1 A 1 0 plus A star 0 1 A star 0 1 A 0 1 A 1 1 A 1 1. Okay, so now let's try to simplify this. So if we try to pull out A star 0 0 A 1 0, okay, let's see where can we pull out A star 0 0 A 1 0. If I pull out, I mean, you can do it in different ways, right? I'm just seeing. Okay, let's suppose I do that. Okay, you can do it in your own ways. Suppose I do A star 0 0 into A 1 0. Take it as common. Then this leaves me with magnitude A naught square, right, for this term. And from here, if I pick A star 0 0 A 1 0, then that leaves me with A star 0 magnitude of A naught 1 square plus. Then what do you have? So these two terms are gone. Okay, we have accounted for them. Again, let's now look at magnitude A naught not. Okay, so A star 0 1 into A 1 1. Suppose I pick into A 1 1. Suppose I pick A star 0 1 A 1 1. Then I get magnitude A naught square from this one. Plus, then from this guy, what happens? A star 0 1 A 1 1. So you get magnitude A naught 1 square, right? So this is magnitude A naught square plus magnitude A naught 1 square is common, and then you get A star 0 0 into A 1 0 plus A star 0 1 into A 1 1. Now this, of course, is simply the norm of, again, A naught star. So this quantity is just 1. If you look at this other one, right? This is like taking the inner product of A naught star with actually A 1 star, right? Because that will be like A star 0 0 into A 1 0 plus A star 0 1 into A 1 1. Okay, and this we know, right, that these two vectors are orthogonal, right? And therefore this is the inner product of A naught star with A 1 star. And therefore this is 0, right? And therefore this product is 0. Okay, so the same way, right, I'll simply leave it to you as an exercise to show that these A star KLs, right, as constructed, okay, which is like, when they come as AK star AL star transpose as constructed, form a 2D orthonormal basis. Okay, so of course, it's not like these matrices are orthonormal. Okay, they form an orthonormal basis, which then means that you should be able to which means that you can actually expand an image. Suppose I give you a 2D image now. So what you can effectively do is you can actually represent it as some double sum over some VKL. Again, your notion of transform coefficient now for a 2D. Now, right, I mean, there are, of course, other interpretations to all of this, right? I'll come to them one by one, okay? There is a larger framework under which they all fit in, but then I thought I'll go kind of step by step. So, VKL into A star KL, where this K and L will go over the size of whatever. V will have the same size as U, okay? And this VKLs can again be found as inner product of U with, A star KL. And that you can show. Then if you take this, then you can take this. So if you use this expansion, that is double sum over KL, VKL. Suppose I take some AMN, right? A star KL, and then suppose I take the inner product with some AMN, where M is not equal to K, N is not equal to L, then you can see that, right, this whole thing will kind of expand out. Okay, so it will be like V0 0. Right? I mean, you can see that. Now, suppose you have, let's say, 0 to 1. Okay, let's just take the simplest case. Then this will be like V0 0 A star. So it will be like inner product V0 0 A star 0 0. Let's say A star. Suppose you take whatever. No, you want to take let's say 1 1. Suppose. Okay, then you will have plus inner product V01 A star 01 inner product A star, what is it? We took 11 plus inner product V10 A star 10 A star 11 plus inner product V11 A star 11 A star 11, right? And we know that out of all this, right, because of the fact that this is the same as V00 will come out, right, into inner product of this plus V01 into inner product, and we know that the inner product of all these guys is 0, right, because they are not identical. Okay, so one thing that maybe I want to write here is that this A star KL inner product with A star Mn, right, is equal to 1 if K equals M, N equals L, 0 otherwise. So which means that this inner product, this goes to 0, this goes to 0. The only guy that will survive is V11, right? So which is why VKL, right, can be found as inner product of U with A star KL, right? And that can be used in turn for expanding U. Okay. Now at this point of time, right, it may still not, right, it may still look slightly murky. That why is all this happening? Right? So this all is tied to a notion of separability and so on, right, which we will see down the line. Okay.